Hello students. So now in this session we'll be doing about second order high pass filter. So already we've done first order low pass filter and first order high pass filter was an assignment. In the previous session we've done second order low pass filter. So this class we'll see what is second order high pass filter and what is the transfer function for the second order high pass filter. So we've already seen in general, second order filter has got a general circuit with a general expression wherein only the R and C places get swapped so that when I have series R and parallel capacitor, the circuit behaves like a low pass filter, and series capacitor and a parallel R, the circuit behaves like a high pass filter. So now since this is an high pass filter, the capacitors will be in series position and all the resistors will be in the parallel position. So here y1 and y2 is taken as SC and y3 and y4 is taken as 1 by R being admittance. So this is the circuit, and the general order second order filter equation is V naught by Vi is equal to A naught y1 y2 by y1 plus y2 into y4 plus y4 into y1 plus y2 plus y3 plus y2 y3 into 1 minus A naught. So you already derived this in general order equation. Now the only thing we are supposed to do is substitute what are the values of y1 and y2 as per this circuit. So in this circuit, y1 and y2 are nothing but sorry. Okay. So in this circuit, y1 and y2 are nothing but capacitors. Y3 and y4 are resistors. So substituting A naught into S square C square plus y1 y2 will be once again S square C square. Y4 which is 1 by R, so 1 by R into y1 plus y2 plus y3. y1 and y2 will be 2 into SC and y3 is 1 by R. So 2 SC plus 1 by R, and here it is y2 y3, so SC by R into 1 minus A naught. So in next step, what I'm doing is I'm splitting all the components out of the bracket and then finding the common LCM. So S square, I'll be getting A naught S square C square divided by S square C square plus 2 SC by R plus 1 by R square. That is splitting this bracket. And then once again SC by R minus SC A naught by R. And then taking R square as common LCM, you'll be getting this step. Now next step is moving this R square to the numerator. So this, when I move to the numerator, V naught of S by VA of S is equal to A naught into S square R square C square divided by S square R square C square plus RSC. Since I have two RSC over here already, and then one more RSC which is 3 times of RSC, and this is also RSC. So clubbing this and this component, I'll be getting RSC into 3 minus A naught plus 1. So now simplification of this for that. So moving this R square C square to the denominator, you'll be getting A naught S square divided by S square plus 3 minus A naught into S divided by RC plus 1 by R square plus C square. Now since this being a high pass filter, the cutoff frequency is called lower order cutoff frequency denoted by omega L. L stands for lower order. So omega L is taken as 1 by RC. So wherever I have 1 by RC, I can substitute it as omega L. So in this equation, substituting 1 by RC as omega L, we'll be getting A naught S square by S square plus 3 minus A naught into this 1 by RC term becomes omega L. Similarly, here I have 1 by R square C square which will become omega L square. Okay, so I'm moving this S square also to denominator. So ultimately H of S is equal to A naught by 1 plus 3 minus A naught omega L by S plus omega L by S square. So but in general, we take the transfer function as this one, which is A naught S square divided by S square plus alpha omega LS plus omega L square. You've already seen what is alpha in the previous low pass filter, where alpha is called the damping coefficient, and omega L is the lower cutoff frequency in radians per second. A naught will be the gain. So this is the equation for second order high pass filter, transfer function of second order high pass filter. So now what we will do is we'll try to substitute SS j omega and get the general equation for exclusively Butterworth filter. If you remember, we've already discussed, depending on this value of alpha, we can classify the filter as Bessel, Butterworth and Chebyshev, out of which Butterworth filter has the flattest passband. So that is the more commonly used type of filter. So for Butterworth filter, alpha value is 1.414, which is root 2. So we'll find what is the transfer function for Butterworth filter. So what I'm doing is substituting S as j omega. So you'll be getting A naught j omega whole square plus by S square is j omega square. Here I have one S component j omega plus omega L square. And then, so here j square will become minus 1. Here also j square will become minus 1. So I'm rewriting this minus a naught omega square divided by minus omega square plus j omega alpha omega L plus omega L square. So moving this omega square to the denominator, minus a naught divided by minus 1 plus j times of alpha omega L by omega divided by omega L by omega the whole square. Now this, what I'm going to do is I'm going to split this as real part and imaginary part. So in this case, this minus 1 plus omega L by omega the whole square is the real part, and this j alpha into omega L by omega is the imaginary part. That is what I've done here. And we've already seen for Butterworth filter, alpha value is 1.414, which is root 2. So substituting 20, and I'm finding the decibel value. So 20 log of h of j omega is 20 log of, since this is absolute value, the negative sign disappears here. So I don't have any negative sign. A naught divided by modulus of this value will be root of a square, real part square plus imaginary part square. So real part being this omega L by omega the whole square minus 1 the whole square plus omega L by omega the whole square. So simplifying this further, this we'll have to split into a minus b the whole square formulae. And then when you're doing that, this 2 omega L square by omega square cancels out. So ultimately you'll be getting 20 log of a naught divided by root of 1 plus omega L by omega to the power 4. So this to the power 4 can be written as 2 into 2. This is already done in the low pass filter. So 2 into 2, where 2 signifies the second order filter. So in general, if I want for nth order filter, we'll be getting h of j omega by a naught is equal to 1 divided by root of 1 plus omega L by omega to the power 2n, where n refers the order of the filter. Now, this is with angular frequency. Same thing when I apply for the linear frequency, I'll be getting 1 divided by root of fl by f to the power 2n. So this is the transfer function for exclusively Butterworth second order high pass filter. Now, in case if you are asked to find the expression, that is transfer function for any Bessel or Chebyshev filter, the only thing you have to do is substitute the value of alpha as the corresponding one. That is 1.06 or 1.732 for Chebyshev, that is root 3. And then you will have to simplify this further, right? So with this, the introduction for filter, low pass filter and high pass filter, that is first and second order, all are done with this session. So next session will be band pass filter and band reject filter. Thank you.